Welcome to the Problemers channel, season 2, episode 8, the episode which I titled Horses and Carrots, Camels and Bananas, because the problem whose solution we will be discussing in this episode can be framed in different ways, and we'll get to these different ways later on in this episode. And right now, as a friendly reminder, if you are joining our channel in the middle of the season, we highly recommend that you go to the home page of this channel, and in the channel's trailer section find the episode titled The Problemers Channel How To, and watch that episode in its entirety, because in that episode we explain and motivate why and what we do on this channel. Also, we recommend that our readers resist the temptation to practice mathematics incorrectly and instead choose to practice mathematics correctly, as was explained in season 1, episode 2. And if you were able to solve the mathematical problem S2E8 completely and on your own, then it is by all means a good idea to watch this episode in its entirety from the beginning to the end and compare your solution to ours. And if you think that your solution is in some way better than our solution, then by all means, feel free to share your solution with us, and we will find the place and the time to share your solution with your permission and with full credit with our community. And if you were not able to solve this problem completely and entirely on your own, then as we explained in season 1, episode 2, it is a good idea to not watch this episode in its entirety from start to finish, but instead to watch it in chunks according to the minimum viable principle. According to this principle, it is a good idea to watch only the smallest amount of information that we present in this episode that will make you go, aha, I see what is going on. At which point, we suggest that you hit the pause button on this video, walk away from the computer, and try to solve this problem from that point onward all the way to the end on your own. If you cannot do that, then again we recommend that you keep doing or keep running this minimum viable cycle until you can generate a solution of this problem all the way to the end completely and on your own. Meanwhile, as a refresher, in the mathematical problem S2E8, we're told that once upon a time there lived a farmer who collected a harvest of 3,000 carrots, and the farmer's wife told him, Johnny, we have our daughter's wedding coming up real soon. It is a good idea if you go to the nearest market and sell as many carrots as you can. And there lies the intellectual challenge of this problem. We're told that the farmer has one horse, and that horse can carry at most at any one time 1,000 carrots. And further, the constraint is that for every mile traveled, the horse consumes precisely 1 carrot. In order to make sure that everyone is on the same page, the fact that the horse consumes 1 carrot per each mile traveled means that the horse will consume 1 carrot per mile if it travels from the farm F towards the market M, and the horse will consume 1 carrot per mile traveled in the direction from the market towards the farm F. Thus, under these constraints, we are asked to generate a scheme or an algorithm or a way for a farmer to deliver as many carrots from the farm F to the nearest market M that is located 1,000 miles away from the farm as possible. In real time, we remember that mathematics, first of all, is an art. Mathematics is an art of telling a story of how and why. And as authors of such a story, we're on the hook to demonstrate creativity, ingenuity, improvisational skills, and as we mentioned in the how-to episode on this channel, we're first and foremost are interested in the process of how the search for a solution of a technical problem may unfold and how exactly we can arrive at an answer in this or that problem. Consequently, to wrap our brain around the mathematical problem S2M10 in order to scale or size up the challenge that lies ahead, we may think as follows. The fact that the horse can carry at most 1,000 carats at a time means that this horse can carry 0 carats, 1 carat, or 2 carats, or 3 carats, or 59 carats, or 739 carats. And as soon as we put, for example, 1001 carat on the cart that is being pulled by this horse, the horse, according to the constraint of the problem, will not be able to move, and we will have to take this 1 carat off the cart. Consequently, because we're asked to deliver the maximal number of carats from the farm F to the market M that is 1,000 miles away, it makes sense to not underload the horse by putting, for example, 615 carats on the cart, but by putting all 1,000 carats on the cart. As such, let's say for experimentation purposes, we loaded our cart with 1,000 carats, and we travel 1,000 miles from the farm F to the market M. As we travel, we're told that the horse consumes 1 carat per each mile traveled, which means that during this first trip from the farm F to the market M, the horse will consume how many carats? Exactly. On our first leg from the farm F to the market M, at the rate of 1 carat per mile, the horse will consume 1,000 carats, and we will arrive at the market with precisely 0 carats. And at this point, it is not really clear how, by honoring the constraints of this problem, we can ever get back from the market M to the farm F, because we have precisely 0 carats. And remember that even when the horse travels back from the market to the farm, it still needs or wants to eat 1 carat for each mile traveled. Here, if we think a little bit, we may realize that under the artistic license of, let's say, theoretical physics, we may creatively or craftily bend the space and, so to speak, put the market M right on top of the farm, let the horsey, the farmer, and the cart jump off the market directly into the farm, and then unfold the space. And at that point, we will find ourselves back at the farm with how many carats left at our disposal. Well, at that point, at our disposal, we will have 3,000 minus 1,000, precisely 2,000 carats left. 2,000, I'll mark them with blue chalk. And at this point, we think that we can repeat the same experiment again. That is, we load 1,000 carats onto the cart. 1,000 carats onto the cart. We travel 1,000 miles towards the market. We consume 1,000 carats again, and we arrive with precisely 0 carats to the market. We again craftily bend the space and put the market right on top of the farm, let the farmer, the horsey, and the cart jump off the market directly into the farm. Unbend the space, and we find ourselves back at the farm with how many carats? 2,000 minus 1,000, 1,000 carats. At which point we know that if we load all 1,000 carats onto the cart, we will have no more carats left at the farm. We travel 1,000 miles towards the market. At the specified rate of 1 carat per mile, we consume precisely 1,000 carats, and we arrive at the market again with 0 carats. And when we step back and look at the result of this thought experiment, we realize that what we have on our hands is our first. Yes, what we have on our hands is our first failure. And as counterintuitive as it may sound, failures in mathematics, theoretical physics, and computer science are just as, if not more important than successes. As one of my math professors used to say, mess things up with style, which means that when we make a mistake or face a failure in mathematics, theoretical physics, or computer science, and invariably and inevitably we will make mistakes and we will face failures in hard sciences, we want to do it in such a way so as to learn the maximum possible information from that mistake or from that failure so that on the next iteration of attacking this or that problem, we avoid making this mistake or we avoid arriving at that failure. However, as Albert Einstein famously said, a sheer definition of madness is doing the same thing over and over again and expecting a different result. Right now, the result of our first thought experiment is a failure. Consequently, if we want to achieve a success in solving this problem, we cannot repeat the same experiment over and over again and expect a different result, which means that we have to shake our reasoning in some way so as to make some progress in searching for a solution of this problem. And that is one of the reasons why I brought this problem to your attention. So far, we haven't done anything more complicated than using only the arithmetic operation of subtraction. From 3,000 carats, we subtracted 1,000 carats to arrive at 2,000 carats. At 2,000 carats, we subtracted another 1,000 carats to arrive at 1,000 carats, and so on. And here, on the one hand, some number of students will, unfortunately or amazingly enough, already give up and say, Roman, look, you gave us some nonsense mathematical problem that cannot even be solved. You just showed us that precisely 0 carats can be delivered from the farm to the market. On the other hand, uh, this problem that is very straightforward and that is at the middle school or perhaps even pre-middle school level shows that genuine or correct mathematical problems that are very straightforward and a very low level, so to speak, already carry some mysterious substance in them that puts front and forward the following idea. In grown-up mathematics, we want to possess or develop and nurture the following personal traits: the mathematical intellectual stamina and the mathematical intellectual resilience. What is intellectual stamina and what is intellectual resilience? Intellectual stamina and intellectual resilience is an ability to find the willpower in oneself to not give up in the face of a failure and to dig one's heels in and still fight the academic fight and look for a different angle of attack at a problem that we failed to solve during the first take. As such, taking into consideration everything that I said so far, how can we change our angle of view on our first and failed thought experiment? In real time, different people will obviously and thankfully think in different ways, but as we struggle with this problem, the following happy thought may occur to us. What if we still use the maximal capacity of the horse and we still load 1,000 carats onto the cart, but instead of traveling all the way to the market, we stop somewhere midway and organize a temporary storage facility where we deposit some number of carrots. Maybe we can move the carrots closer to the market that way. Again, we do not know what lies ahead, so the only thing that we can do is try. As such, let's say I'll make a schematic drawing somewhere else on the board. Here we still have the same farm F. Some 1,000 miles away we have the market M. That is 1,000 miles away from the farm, and 1,000 miles is a number that is so inviting that pretty much many people on the first go will say, okay, what if we cut this distance in half and try to deposit some carrots 500 miles away from the farm at, let's say, here 500 mile marker. What will happen then? Well, we still have 3,000 carrots. We still have 3,000 carrots at the farm. We load again our cart to its maximal capacity of 1,000 carrots. 1,000 carrots. And we travel, but this time instead of going all the way to the market, we stop at the 500 mile mark, and then we analyze what just transpired. At the given rate of 1 carrot per mile, our horse will consume how many? Our horse will consume 500 carrots, so 1,000 carrots minus 500 carrots will be equal to 500 carrots again, carrots, and at the 500 mile mark we will have 500 carrots on the way from the farm to the market. How many carrots can we deposit in this case? Well, if we want to honor the constraint of the problem that is given right here, that the horse eats 1 carrot per mile regardless of the direction in which it travels, then we realize that at the 500 mile mark, right now, even though we still have 500 carrots on the cart, we cannot deposit any carrots because we will need all these 500 carrots to do what? We will need all these 500 carrots in order to get back to the farm, and that is what we do. Here we load 500 carrots onto the cart. The 500 carrots go onto the cart, and we travel 500 miles all the way back to the farm. We consume these 500 carrots. We arrive at the farm with an empty cart. Our farm right now has how many? 3,000 minus 1,000, 2,000 carrots. We still have 2,000 carrots left at the farm. And we realize that if we will keep shuffling the carrots between the farm and the 500 mile marker in the way described over here, again, we will not move any carrots closer to the market. And this thought experiment is our second failure, but that failure is correct. That failure is a better failure. Why is that failure a better failure than our first failure? Our second failure is a better failure than the first failure because at least this time we managed to make a round trip from the farm to the temporary storage facility, honoring the constraints of the problem. In other words, in our first failed thought experiment, by the time we arrived at the market, we did not have any carrots to return back. But now, with our second attempt and with the second failure, we managed to fail gracefully or with style, because still we honor the constraint. The horse eats 1 carrot per mile regardless of the direction of its travel. So now we need to step back a little, inhale the results of our second or better failure, and try to shake our line of reasoning one more time or several more times in order to make some headway, in order to make some progress of moving at least a little bit, some number, 1 carat closer to the market. Excellent. As we look for a creative ways to shake our lines of reasonings that failed so far, some of our viewers or some of our students can say, Roman, look, you talked about the artistic license of theoretical physics and bending the space creatively. Why don't we, instead of bending the space in such a way so as to bring the market to the farm, we just begin with bending the space in such a way that we bring the farm to the market, and in one fell swoop we deliver all 3,000 carats to the market that way. That is actually a very good idea, and those of our viewers who came up with that idea deserve one medallion with the out-of-the-box thinker, the mascot of our channel. Unfortunately, in this problem, we are not allowed to bend the space that way. We need to operate in terms of the traditional line segments that separate the farm and the market. But in the near future, in computer science, we will solve a problem that allows a very elegant and very beautiful solution precisely when we bend space and we curl a line segment into a circle, as we shall see in one of the future episodes. Meanwhile, I erase our old experiments. If you need them, you can rewind and go back to them. That way, here I made the distance between the farm and the market on the board a little bit longer because we'll need more space. And again, as we analyze our failures, why we failed, and what can we do so that on the next iteration of attacking the solution of this problem, we do not run into the same problems and we do not run into the same failures, the following happy thought may occur to us. By analyzing what happened in our second or better failure, we may come to the idea that we need to move the location of the first storage facility a little bit closer to the farm, and that distance should be definitely less than 1/2 of the capacity of the horse, but this time measured in miles, precisely because our horse eats 1 carat per mile. Now, the way we come up with these numbers doesn't have any hard or specific science to it. Again, we are experimenting, and when we experiment, we do not know any better. We just come up with arbitrary numbers, and one way to move our failed first storage facility from the previous experiment is to, for example, let's say we put this first storage facility at, let's say, 300 mile mark, and we think that there is plenty of space left between the storage facility number 1. We throw another 300-mile distance over here at, let's say, 600-mile mark. At 600-mile mark, we organize the storage facility number 2. And because this is an experiment, we do not know what will happen. All we have to do is run down the numbers and analyze where will this idea lead. To that end, we reason as follows. At the farm, we still have 3,000 carats. We load all 1,000 carats, onto the cart. We travel 300 miles to our first storage facility, and on that leg of our journey, we consume how many? Apparently, given the rate at which the horse consumes the carats in order to cover 1 mile, we will consume 300 carats, so 1,000 carats minus 300 carats comes out to 700 carats. 700 carats. So we arrive at our storage facility with 700 carats. Now, how many carats can we legally deposit at our storage facility 1 that is located at 300-mile marker away from the farm if we want to honor the constraint that we need to still have enough carats to feed the horse so it can get back to the farm? Well, we already know by the time actually we depart from the farm that on the way back we will consume another 300 carats. So from the 700 carats that we have on our forward journey, from this number we subtract another 300 carats and we arrive at 400 carats. 400 carats. In other words, by the time we travel back, we grab 300 carats with us, and that means that how many carats can we deposit at our storage facility number 1? Precisely, we can deposit 400 carats. 400 carats on after we arrive at the storage facility on the forward trip. We grab 300 carats for the trip backwards towards the farm, and by the time we load 300 carats onto the cart, we consume 300 carats and we arrive at the farm with nothing left in the tank, so to speak. And how many carats do we have? We have 3,000 minus 1,000 is 2,000 carats still. So we have 2,000 carats at the farm to transport, but so far we feel that we're making some progress because at the expense of 300 and 300 or 600 carats, we managed to move 400 carats 300 miles closer to the market. And how many trips have we made so far? Well, 1 trip towards the storage facility number 1 and 1 trip away from the storage facility number 1 towards the farm, for a total of 2 trips. We'll write down, for example, 2 trips over here. We'll say we made 2 trips. Now, as we analyze the result of what just transpired, we still understand that if we have 2,000 carats at the farm, then we can repeat exactly the same experiment by loading 1,000 carats onto the cart, traveling towards the first storage facility that is 300 miles away from the market, spending 300 carats to do so, and then depositing another 400 carats at the storage facility number 1, so that we have another 300 carats to get back from the storage facility number 1 to the farm. That will be this trip number 2, trips number 3 and 4. So that's another 2 trips. In another 2 trips, we move another 400 carats closer to the market. And by the time we do that, how many carats we will have left? Minus 1,000 carats. Minus 1,000 carats comes down to 1,000 carats. Except that this time, as we depart from the farm F, we know we're not coming back towards the farm after we reach the storage facility, on the way towards the market. We'll load the entire 1,000 carats onto the cart, travel 300 miles towards the market to the first storage facility. On that journey, we spend how many? We spend 300 on that journey. We spend 300 carats. 300 carats. 1,000 minus 300 carats comes down to 700 carats. So after the trip number 700 carats, after the trip number 5, one trip for a total of 5 trips. For a total of 5 trips, we will have accumulated how many carats at the storage facility number 1? Well, let us count together. After 5 trips, as described, we will have 400 and 400 is 800, 800 plus 700, we will have 1500 carats. We will have 1500 carats after 5 back and forth trips at the storage facility number 1 that is located 300 miles away from the farm. Here we want to note that again on this channel we want to bring front and center and nurture and develop out-of-the-box thinking. So what type of out-of-the-box thinking we can exhibit over here as we try to move our carats closer to the market at 300-meter mark? Well, for example, after we make our first pair of trips, 1,000 carats onto the cart, first trip towards the storage facility number 1, and the second trip back from the storage facility number 1 to the market, we already know that for the second 1,000 carats that we will be transporting the same way, we do not really have to carry all these carats with us on our cart. This idea may or may not pan out. This idea may or may not be useful, but still, because we like to think out of the box, this is one idea that we generate and we write it down just in case maybe it will become useful later. As such, for example, even on the first and the second moves of 1,000 carats from the market to the storage facility number 1, what we can do is the following. We can feed 1 carat to the horse and we can drop the second carat on the ground, so to speak. That way, as we cover the distance of 300 miles, we arrive at the 300-mile marker at storage facility number 1 with how many carats? Well, because we consume, so to speak, 2 carats per mile over 300 miles, this will be 600 carats. We arrive with 400 carats at the storage facility number 1, and at this point we have nothing left on the cart. But as we turn around, we now begin consuming the carats that we dropped on the ground. Of course, this is a mathematical idealization. We think that there are no animals, there are no thieves on the trips that the farmer makes and so on. But it is a worthy technical idea, so that the horse, in theory, doesn't have to work as hard as it hauls carats between the farm and the storage facility number 1 during what? The first trip forward and backward, and the second attempt to move 1,000 carats to the storage facility number 1. On our 5th trip, when we move 1,000 carats to the storage facility number 1, we already should not be dropping anything on the ground. We should be only feeding the carats to the horse and arrive at the storage facility number 1 that is located 300 miles away from the farm with 700 carats, making for 1,500 carats in total. Now, as we enjoy a little bit of success, we realize that economically, of course, that was not very pleasant or very favorable. We actually, out of 3,000 carats, we spent, so to speak, 1/2, 1,500 carats, and we only moved these 1,500 carats 300 miles closer to the farm. So we actually spent 1/2 of all the carats, but we came closer less than 1/3 to the market. Either way, we now want to analyze what will happen if we try to move this 1,000 carats towards the second storage facility, that is located 300 miles away from the first storage facility, and that is located at 600-mile marker away from the farm. Here, the process in some sense is recursive with respect to the process that unfolded on our first attempt to move the carrots from the farm to the storage facility number 1, except that instead of 3,000 carrots, we now have only 1,500 carrots. And what does that mean? That means that every time that we load our horse to its maximal capacity, how many trips back and forth we will be making? Well, instead of 5 trips that we made in the first experiment, here we will be making only how many? Let me write it down with a different color. Here we will be making only, let me see, here we will be making only 3 trips. 3 trips. Let's see what these trips are. On the first trip, we will load 1,000 carrots onto the cart, travel 300 miles from the storage facility number 1 towards the storage facility number 2. Here we can utilize, in a way to ease maybe some computations to some extent, our lightweight out-of-the-box idea of eating 1 carrot and dropping 1 carrot on the ground, because we know we will be coming back from the storage facility number 2 towards the storage facility number 1. That way we spend or consume how many? 300 times 2 is 600. We will be consuming 600 carrots, and we will be arriving at the storage facility number 2 with 1,000 minus 600 comes down to 400 carrots on the first trip from service storage facility number 1 towards the storage facility number 2. Then we turn around and travel back from the storage facility number 2 towards the storage facility number 1, but because we cleverly dropped 1 carrot on the ground at each proper location, the horse picks up these carrots, eats them at 1 carrot per mile rate, and arrives back on the second trip with nothing on the cart. At this point, how many carrots will be left at the storage facility number 1? Well, at this point, we will have 1,500 carrots minus 1,000 carrots. There will be 500 carrots left. 500 carrots left after 2 forward and backward trips at the storage facility number 1. And what our choice is at this point? Well, it doesn't take much to realize that our only choice is to load the entire amount of 500 carrots onto the cart, travel from the storage facility number 1 to the storage facility number 2 with 500 carrots. This time we do not engage into any clever tricks of eating 1 carrot and dropping 1 carrot on the ground. We keep everything on the cart. On that third leg of the journey from the storage facility 1 to the storage facility 2, we consume how many? 300 carrots. And by the time we arrive at the storage facility number 2, we will have how many carrots on the cart? 500 minus 300 minus 300 carrots. It will be 200 carrots left. So here we write down we have 200 carrots at the storage facility number 2 that is located 300 miles away from the storage facility number 1, and that is located 600 miles away from the farm. At this point, after 5, let's write it down here, 5 plus 3, after 8 trips back and forth as explained above, how many carrots do we have accumulated in the storage facility number 2. After all these trips at the storage facility number 2, we will have 200 plus 400 will be 600 carats at storage facility number 2. Now, how far is the storage facility number 2 away from the market? Well, 1000 minus 600 comes down to 400, so this distance right here is 400 miles. Now, in a way, recursively, we still are solving the same, essentially the same problem of having 600 carats instead of 1500 carats and instead of 3000 carats at the corresponding locations. But now we want to transport the 600 carats from the storage facility number 2 towards the market. What are our choices? Well, in order to find an optimal solution, our only choice is to load everything that we have, load all 600 carats onto the cart, and travel with 600 carats towards the market while consuming 1 carat per mile, and thus spending how many? 400 carats. Now, but we have 600 carats on the cart, so 600 carats minus 400 carats comes down to 200 carats. So now 200 carats. We'll put this to a box of its own after making 5 plus 3 plus 1, 8 plus 1, 9 trips. 9 trips. We actually managed to deliver 200 carats from the farm to the market, honoring all the constraints of the problem so far. And amazingly enough, a mere 15 or 20 minutes ago, some students said this problem is impossible to solve, yet 15 or 20 minutes later, we managed actually to find a legal way that honors all the constraints of the problem to deliver 200 carats to the market. But now the question is this number optimal? In other words, in this case, we partitioned the distance between the farm and the market as follows: 300 plus 300 plus 400 equals 1000. Of course, this is all miles, just to be pedantic about the units of measurement. 300 plus 300 plus 400, and partitioning a set means that we divide that set into subsets in such a way that there are no gaps and no overlaps between the subsets, which means that in this case we partition the distance, the line segment distance between the farm F and the market M, into 3 line segments that do not overlap and that do not have any gaps between them. And the question now that we managed to find at least one scheme to deliver more than 0 carats from the farm to the market, honoring all the constraints of the problem, is the following: is that number optimal, or does there exist another partitioning or another delivery scheme that will deliver or allow the farmer to bring more than 200 carats from the farm to the market? As we enjoy some success with finding a way to deliver more than 0 carats from the farm to the market, we conduct more experiments trying to find a more optimal solution that will allow us to deliver more carats from the farm to the market. In real time, different people will, of course, do different things, but here, in order to show the idea that a search for a solution of a mathematical problem is never straightforward. Let us say that for experimentation purposes, we partition our distance between the farm and the market in such a way so as to move the storage facilities a little bit closer to the market, and we want to see what will happen then. For example, let us say that we partition our distance from the farm to the market as follows: 350 plus 350 plus 300, which of course equals to 1000, and all these numbers are shown here in miles. That means that the first storage facility is located 350 miles away from the farm. The second storage facility is located 700 miles away from the farm, and the 300 miles is the distance that separates the storage facility number 2 from the market. Then we already know how the numbers play out. If we begin at the farm with 3,000 carats, then in the first 2 trips to the storage facility number 1 and back from the storage facility number 1 to the farm, we will deliver how many? 350 plus 350 is 700. 1000 minus 700 comes out to 300 carats. On the second trip to the storage facility number 1 and back, we will also deliver 300 carats to the storage facility number 1, and with the remaining 1000 we will spend 350 carats feeding the horse to get from the farm to the storage facility number 1, and we will deliver exactly 650 carats for a total of 1250 carats located at storage facility number 1. Now we see that if we load 1000 carats onto the cart at the storage facility number 1, we will be able to make the trip towards the storage facility number 2 that is located at 700 miles away from the farm, and on the way back we will be able to deposit how many? Again, 300 carats. 300 carats. But what do we see now? We see now that we will have 250 carats left at the storage facility number 1, and this is obviously not enough for us to get to the storage facility number 2 in the first place. So this already is shaping up to be another failure. We may think over here, okay, how many carats do we need to have at the storage facility number 1 so we can at least get to the storage facility number 2? Well, we need extra 100 carats. Where do these carats come from? Well, we may think that instead of depositing 300 carats at the storage facility number 2, we will deposit only 200 carats. We'll deposit only 200 carats. We will bring 100 carats back. At this point, we will have 350 carats at the storage facility number 1, and then we will be able at least to get to the storage facility number 2, but at the storage facility number 2 more trouble awaits because we have only 200 carats there. And how many carats do we need? Because there are 300 miles separates the storage facility number 2 from the market, and the horse consumes precisely 1 carat per mile, it follows that we need 300 carats to get from the storage facility number 2 to the market, and clearly we do not have that, and this experiment again is shaping up to be a major failure as well, and we need to look for a different delivery scheme. Here we can switch gears a little bit, and instead of partitioning the distance between the farm and the market in big chunks, we want to experiment with what will happen if we will partition the distance between the farm and the market in much smaller chunks. For example, 1 mile at a time. Very well. We now zoom a lot on the distance between the farm and the market. We partition it into 1 mile segments. 1 mile, let's put it here, 1 mile, mile number 2, mile number 3, mile number 4, and so on. And we would like to investigate what will happen if we will try to move all of our carrots 1 mile at a time in the direction from the farm to the market. As such, for our first move, we load 1,000 carrots onto the cart. We travel 1 mile towards the 1 mile marker. We consume 1 carrot. And how many carrots can we deposit at the 1 mile marker? Well, because we know that we need to eat 1 carrot in order to get back, we deposit exactly 998 carrots at the 1 mile marker. And by the time we arrive back to the farm, we have 2,000 carrots left, and we have made 2 back and forth trips so far. We repeat this operation again. We load 1,000 carrots onto the cart. We move 1,000 carrots 1 mile. We consume 1 carrot. We bring 999 carrots to the 1 mile marker. We deposit 998 carrots there. And we come back from the 1 mile marker towards the farm, where we have 1,000 carrots left. This time, however, we know already that we will be making only one-way trip from the farm to the 1 mile marker, which means that on that trip we'll only consume 1 carrot. We will arrive at the 1 mile marker with 999 carrots, and in total we will have 2,995 carrots at the 1 mile marker after the first move. In other words, right now we see that in order to move about 3,000 carrots 1 mile from the farm towards the market, the cost of that move is 5 carrots per mile, because here we make exactly 5 trips back and forth. At that point, we do the same thing with 2,995 carrots, as we try to move all that number of carrots 1 mile forward towards the market, repeating the same 5 trips at a time. And again, we see that at the 2 mile marker, by the same logic, we will have how many carrots? Well, at this point we will have 2,990 carrots. And if we repeat that process of moving 2,990 carrots 1 mile towards the market, we will have how many? At the 3 mile marker, we will have 2,985 carrots, and so on. And at this point, we can already argue that at the integral mile marker number x, there will be how many carrots? Well, we will see that at the integral marker number x, where x is a stand-in for 1, 2, 3, 4, 5, and so on, we should have the initial amount, that is 3,000 carrots, minus 5 times x. And here, units of measurements wise, what do we have? 5 is measured in carrots per mile, so we will have carrots minus carrots per mile times miles. The number x is measured in miles. Miles and miles cancel out, and we have carrots minus carrots, which comes out to carrots. Now, will this process go on indefinitely? If we think about it, then we realize that no, this process cannot possibly go indefinitely, because with the numbers no doubt carefully dialed in with this problem, sooner or later the horse will eat the number of carrots that will amount to its maximal capacity, or 1,000 carrots. And when will that happen? At which integral mile marker will this event occur? Well, we know how to answer that question. We just have to construct an equation which says 5 times x equals 1,000. Again, units of measurement wise, we have carats per mile times miles comes out to carats, 1,000 carats. In this case, this equation over the set of positive whole numbers is solved quite nicely. X comes out to 200 miles. And that means that at the marker that reads 200, this is obviously horribly out of proportion, but just for demonstration purposes, we realize that at the mark of 200 miles, we will have how many carats? 3,000 minus 5 times 200 minus 1,000 comes out to 2,000 carats. Let me write this number down with a red chalk. We will have 2,000 carats. 2,000 carats. Now, our objective is still the same. We want to see what will happen if we will try to move these 2,000 carats towards the market, still again 1 mile at a time. Here we will do exactly the same operation as we did previously when we had 3,000 carats to move, but fundamentally very little changes. We load 1,000 carats. We load 1,000 carats onto the cart. We travel 1 mile. 1 mile. We arrive at this 1 mile marker with how many? With 999 carats. We deposit there 998 carats. We use 1 carat to come back, and at this point we pick up the remaining 1,000 carats. We know that this will be a one-way trip. We will not be coming back. So now in just 3 trips, we move 2,000 carats 1 mile closer to the market. And how many carats we will have there? Well, at this point we will have 998 carats, and in total this will be 1,997 carats at the marker that is 1 mile past the 200-mile marker. Again, by analogy with the process that unfolded in our previous move, we reason that at the integral mile marker y, how many carats will be at this position? Well, it's not too difficult to realize that the number of carats at this position will be 2,000, again in carats, minus what is the cost of moving whatever number of carats we have at this particular integral marker 1 mile closer to the market. Well, because now we're making only 3 trips, not 5, but 3 trips, and on each such trip we consume 1 carat. It stands to reason that at this point the cost of moving the carats that we have 1 mile closer to the market is 3 carats per mile, and we need to multiply that cost by the integral mile marker y. That is how many carats will be found at the temporary storage facility marked by the integral marker, mile marker y. Now, will this process of delivering here, it will be 1997. Here we will have carats, 1994 carats. Here we will have 1991 carats, and so on. Will this process go on indefinitely? Thinking about it, we again realize that no, this process cannot possibly go indefinitely, because sooner or later the horse will eat through the number of carats that is equal to its maximal capacity of 1000 carats. And when will that happen? Well, again, we know how to answer that question. We just have to take our cost of 3 carats per mile, multiply it by y in miles, and equate that number to the maximal capacity of the horse, or 1000 carats. This time we see that over the set of positive whole numbers, this equation does not solve that nicely, because the prime factorization of 1000 does not contain 3. So we need to be careful here and come up with an answer that is slightly below and slightly above 1000. For a smaller number, we have y equals 333. We'll take this as the smaller number, designated with the subscript y sub s for the smaller number. And the larger number that is just above y sub l will be 334. And now we want to analyze what will happen at the mile marker position that corresponds to the y sub s 333, or mile marker y sub l equals to 334. As such, let us analyze how many carats we can deliver from the farm to the market. If we take our first solution of the equation, which designates the mile marker at which we will have precisely about 1000 carats located away from the market at the value that is shown over here, y sub s, s for smaller, 333 miles. In this case, let's mark this guy with the miles too. In this case, since y is equals to 333 miles, 200 plus 333 comes out to, let's say over here, again, this is horribly out of proportion, 533 miles. How many carats will we have at this mile marker? Well, that is easy to figure out. 3 times 333 will be 999, which means that as we move 2000 carats back and forth 1 mile at a time towards the 533 mile marker, we will consume, let's write it down here, 3 times 333. Again, that multiplication should be taken with the corresponding units of measurement into account. So 3 carats per mile times miles equals 999 carats. So that is how many carats we will consume while moving the remaining 2000 carats 1 mile at a time, 3 trips per mile in the direction from the storage facility number 1 towards the market and towards the storage facility number 2. 2000, we can even do this without much effort. 2000 minus 999, so let's write it down. 2000 carats minus 999 carats equals to what? 1,000 and I'm sorry, got too carried away with this one. 1,001 carats. So at the storage facility number 2, that is located 533 miles away from the farm, we will have precisely 1,001 carat. Now let us estimate, actually let us compute precisely the distance from the storage facility number 2 to the market. It's not that difficult to see that 1,000 minus 533 will be 467. In other words, this distance over here, I'll write it down below, will be 467 miles. 467 miles. But at that storage facility number 2, we have 1,001 carats. We know that the maximal capacity of the horse is 1,000 carats. That means that this one extra carat cannot possibly make it onto the cart. And here we have a little bit of a freedom to decide what we want to do with it. In this case, for all the hard work that we have been doing, we take the frivolity of eating 1 carat. And that means that we load 1,000 carats onto the cart and we cut a beeline from the storage facility number 2 towards the market. That distance will be 467 miles. We consume 1 carat per mile on that journey, and that means how many carats we will consume by the time we arrive at the market. Well, the number is easy to compute. 1,000 carats minus 467 carats comes out to 533 carats. So that number, let's highlight it with red, 533 carats is the number of carats that we deliver to the market if we go with the solution of this equation shown over here that is slightly below the 1,000 carat count. Let's write it down. So we have 533 carats if, let's use the same color, if y was chosen to be 333 miles. So in other words, to make sure that everyone is on the same page, if the solution of the equation shown here, 3 times y equals 1,000, is chosen to be slightly smaller, 333. 333 times 3, 999. So all the arithmetic here should be transparent, and that means that that choice for the solution of this equation yields 533 carats delivered to the market. Next, let us run down the numbers. If for the solution of this equation we choose the mile marker 334. Awesome. Now we will run down the numbers if the solution of the equation shown over here is chosen to be slightly more than 1,000. 334 miles, symbolized here with y sub l, where l stands for larger. In this case, let us compute the number of carats that the move of 2,000 carats from the storage facility number 1 will cost us when we go towards the storage facility number 2. That is not that difficult to do. We know that for each 1 mile move from the storage facility number 1 towards the market, the cost is 3 trips at the overall rate of 1 carat per trip. That overall cost is 3 carats per mile, as to compare with 5 carats per mile in the previous move. So here I'll use the yellow marker. Our cost will be, I'll write it down over here, 334 miles times 3 carats per mile will come out to 1,002 carats. Again, in this multiplication, we should understand that miles are multiplied by carats per mile. Mile and mile cancel each other out, and we get carats, and that means that the total cost to move 2,000 carats from the storage facility number 1 towards the second storage facility is 1,002 carats at this time. And that storage facility, again, this is horribly out of scale and out of proportion, but just to make it visually different, we will see that in this version of the solution, the mile marker will be where? 334 plus 200 comes out to 534 miles. Consequently, at the storage facility number 2, that is now temporarily located at the mile marker 534, we will have how many carats? Well, that answer is easy to produce from 2,000 carats. From 2,000 carats, we subtract the total cost, which is 1,002 carats. We subtract 1,002 carats, and we obtain 998 carats. In other words, at the storage facility number 2, that is located 534 miles away from the farm, we will have precisely 998 carats. We can even write it down here at storage facility number 2, which is this guy, storage facility number 2. And now we see that at the storage facility number 2, we have the number of carats that is slightly below the maximal capacity of the horse, which is 1,000 carats. At this point, we pretty much have no choice. We put all 998 carats onto the cart and we haul towards the market. So how many carats we will spend on that final trip? Well, the distance between the storage facility number 2, located here towards the market this time is what? 1,000 minus 534 comes out to 466. So that distance here, I'll write it down above, will be 466 miles. So compared to the previous case, we're a little bit closer. We are a little bit closer to the market, but we have slightly less carats than in the first case when we had 1,001 carats. Consequently, how many carats we will deliver to the market in this case? Well, that answer again is easy to produce. From 998, we subtract 466 carats. Again, that number of 466 carats came from 466 miles that we have to cover times the rate of 1 carat per mile comes out again to 466 carats. And if we do a little bit of arithmetic, we'll obtain what? 532 carats. So here we'll write it down, 532 carats if y is taken to be 334 meters. Clearly, 532 is less than 533. Let's write it down. 532 is less than 533, just in case, carats and carats. Consequently, we choose the larger number of carats delivered to the market because that is precisely what we're asked to do. And now we step back and inhale our problem-solving experience. About 30 minutes ago, some of us thought that this is a mathematical nonsense, impossibility, and Roman is wasting your time. About 15-20 minutes later, we found a way to deliver 200 carrots to the market, and 15 minutes later still, we managed to deliver a whopping 533 carrots. So now the overall question is, can we keep improving the number of carrots that we can deliver to the market, or this is it? And more importantly, how do we know if a solution that we produced is optimal, meaning maximal, or not? This is where the reverse order problem solving approach comes in. So how does the reverse order problem solving approach dovetail into the solution of this particular problem? Well, let us imagine that a mathematical oracle, a perfect logician, and an infallible computationalist put together an optimal delivery scheme, and our farmer executed that delivery scheme. And as the farmer was executing this optimal delivery scheme, someone was taking a movie of the events that unfolded in this particular scenario, and we are privy to watch that movie but in reverse order. What will we see in the first few frames of that movie? In the first few frames of that movie, we will see that the farmer is high-fiving his horse, celebrating the delivery of the maximal number of carrots from the farm to the market. And then we will see that the farmer with his horse is traveling backwards towards the towards the, let's say here, the storage facility number 2. What can we say about the location of the storage facility number 2, and more importantly, the number of carrots that should be there? Well, based on all our partial successes and failures and going back and forth with playing with numbers in this specific case, this is the optimality constraint or optimality idea that we come up with. The distance of the storage facility number 2, let's say from the market or from the farm itself, doesn't matter, and the number of carrots at that storage facility should be dialed in so carefully so as to be 1,000 carrots. Let's write it down. 1,000 carrots, or dearly close to it, because on the last leg of the journey, if there are less than the capacity of the horse carrots at the storage facility 2, then we already know that we lose. And if it's just a little bit more, that is okay. These carrots are admittedly wasted, but as we saw in the previous computation, we still win. And if we apply the same idea and we keep watching that movie in reverse order, we will see that our farmer will arrive at the storage facility number 1 that should have how many carrots? Well, the number of carrots at the storage facility number 1 with these specific numbers, of course, should be dearly close to or exactly equal to twice the maximal payload capacity of the horse, or it should be exactly 2,000 carrots, or a number that is dearly close to it and slightly above. As such, now let us see what will happen if we position our first storage facility at, let's say, X miles away from the farm. We know that the difference between the number of carrots at the farm, which is 3,000 carrots, and the cost in carrots to move these 3,000 carrots towards the storage facility number 1 should be what? Either exactly equals to 2,000 carrots or dearly close to it. So what is the cost of moving these carrots from the farm towards the storage facility number 1? Well, with our 1 mile experiments, we already know that this cost is exactly 5 carats per mile times x measured in miles. Again, miles and miles cancel each other out, and we obtain carats minus carats equals carats. So units of measurement wise, everything squares and converges. And we already know how to solve this equation. We carry 2000 over to this side of equation. Let's say 3000. I will omit the units of measurement and operate in terms of numbers only. Minus 2000. We carry this term to the right hand side of the equal sign. 5 times x, in other words 1000 equals 5 times x, from where x equals to 200, and this time we bring the units of measurement 200 meters, and we realize that the storage facility number 1 should be located at 200-mile marker. Here we observe that if we go back to the neatly and carefully kept paperwork from our previous experiment, where we moved all the carats available 1 mile at a time, we will see that all these moves 1 mile at a time could have been compressed into one big or contiguous, so to speak, move from the farm to the storage facility that is located 200 miles away from the farm. Awesome. Now that we have 2,000 carats precisely, actually the way it worked out, 2,000 carats precisely at the storage facility number 1, we pretty much play the same game as we played over here, but we note carefully that the cost per mile of moving all these 2,000 carats towards the market will not be 5, but from our previous experiments will be what? It will be 3 carats per mile. So let us assume that the distance from the storage facility number 1 to service storage facility number 2 is y miles this time. And what kind of equation will answer the interesting question over here? Well, it's the similar equation to the one that we have over here. 2,000 carats, the difference between 2,000 carats located at the storage facility number 1 and the cost to move all these carats towards the storage facility number 2 should be 1,000 carats, or dearly close to it. And what is this cost? Well, we already know the cost should be 3 carats per mile times y miles. Again, it doesn't take much to deal with this middle school equation that we know comes out to what? 1,000, 2,000 minus 1,000 comes out to 1,000. Carrying this term on to the right hand side of the equal sign, we get 3 times x. And we already know that in this case, because prime factorization of 1,000 contains only 2 primes, 2 and 5, each raised to the 3rd power, we see that there is no 3 in the prime factorization of 1,000. So over the set of whole positive numbers for the number x, we have 2 choices, one slightly below, one slightly above, when put back into the equation. And we know that we take the one that's slightly larger, and that one corresponds to x equals 233 meters. I'm sorry, this should be y in miles, and this should be y in miles. So the y equals to 333. And we see that the storage facility number 2 should be located at what? 200 plus 333, 533 miles. Once we multiply 333 by 3, we did all the arithmetic in the previous segment, we know that there will be precisely 1,001 carats at the storage facility number 2, 1001. The carat the extra carat will never make it into the onto the cart, and we know that in this case we will deliver 1000 minus 467 miles. That is the distance from the storage facility number 2 towards the market. 1000 minus 467 comes down to 533 carats, and this is the answer to this problem with the description of the algorithm given here and in all the previous segments. We understand that we load 1000 carats onto the cart, travel 200 miles, deposit 600 carats at storage facility number 1, come back, pick up the next 1000 carats, back and forth for a total number of 4 trips. Then we come back for the second time. We have only 1000 carats left. We move this 1000 carats towards the storage facility number 1, and so on, as was explained in the previous segment. Now, I titled this episode Horses and Carrots, Camels and Bananas because this problem is fairly well known in the problem solving circles, and it can be formulated in different ways. Horses eating carrots, or horses eating apples, or camels eating bananas in order to travel. And because now we are aware of the reinterpret and conquer problem solving approach, we know that one and the same mathematical essence can be wrapped into all sorts of perhaps flowery language, but all the differences in this potentially flowery language does not make any difference for the mathematical essence of the problem. And this is the essence of the problem. The optimality constraint that we discovered by reasoning about the solution of this problem in reverse order means that the number of carats at the storage facility number 2 should be precisely equal to the maximal capacity of the horse, in this case 1000, or dearly close to it from above. And by the same reasoning, the number of carats that is accumulated in the storage facility number 1 should be exactly twice the maximal payload capacity of the horse, or dearly close to it from above, and so on. But this particular problem can also be reworded slightly so as to not change its essence but to change its result. And at this point we step away from any sort of connection to reality, but more into the world of pure mathematics or even physics. As such, under the constraints of this problem that were described before, the question that we pose this time is not what is the maximal number of carats that the farmer can bring to the market, but we want to know what is the maximal distance that the farmer can travel under the conditions specified. And this second, slightly different but very related problem can be solved by us pretty much instantly, because we already know that if we arrive at the market with a maximally optimal number of 533 carats, and our horse consumes precisely 1 carat per mile, then past the distance of 1000 miles, how many miles can we travel again without worrying about the need to come back at any point in time? Well, it should be clear that we can travel an additional 533 miles, which means that if we measure the distance from the farm to the farthest point that we can get to, given the constraints of the problem of the horse being able to carry at most 1000 carats, and that the horse consumes 1 carat per mile when it travels into either direction, by shuffling carats between the storage facility number 1 and the storage facility number 2, we can now travel at most 1533 miles. However, now that we understand what is going on, we can ask one more question before we call it a day with this problem. Says who that this 3000 carats harvested by our friendly local farmer are it. Maybe these 3,000 carrots is just another storage facility that is temporarily located on the way to the farthest distance that we can travel under the conditions specified. So maybe there are 4,000 carrots or dearly close to it to the left of the 3,000 carrots, and maybe there are 5,000 or dearly close to it carrots to the left of the 4,000 carrots storage facility, and so on. Under these conditions, what are the distances between these storage facilities if we'll continue going to the left, so to speak, indefinitely? Very well. In summary, in order to make sure that everyone understands the solution of the mathematical problem S2M10, the given distance of 1,000 miles between the farm and the market we partition with two storage facilities, the storage facility number 1 and the storage facility number 2. The storage facility number 1 is located 200 miles away from the farm, and the storage facility number 2 is located 333 miles away from the storage facility number 1 and 533 miles away from the farm and 467 miles away from the market. As overall optimal delivery scheme, we move the 3,000 carrots that are located at the farm in precisely 5 forward and backward trips, as shown over here, 1, 2, 3, 4, 5, to the storage facility number 1. During this entire move, because the horse consumes precisely 1 carrot per mile, we spend, so to speak, 1,000 carrots, and at the storage facility number 1, we aggregate 2,000 carrots. Starting from the storage facility number 1, we pretty much repeat the same process, and this time in 3 forward and backward moves. 1, 2, 3. We move the remaining 2,000 carrots towards the storage facility number 2, precisely because the horse consumes 1 carrot per mile. Again, we spend, so to speak, 999 carrots, and at the storage facility number 2, we managed to aggregate 1,001 carrots. But because the maximal payload capacity of the horse is precisely 1,000 carrots, this 1 carrot is not going anywhere, and we gladly eat it for the effort because we deserve it. And starting at the storage facility number 2, we load all 1,000 carrots onto the cart. We move 467 miles towards the market. The horse consumes 467 carrots, and we deliver the maximal possible number of carrots to the market, which is equal to 533. However, because on this channel we like to think out of the box, we step back from this problem and we inquire, says who, that the given 3,000 carrots, shown over here as well, is the farm. No one says that. We are free as problem solvers and analyzers to ponder that these 3,000 carrots are just another storage facility that is located 200 miles away from the storage facility number 1, and to the left of these 3,000 carrots there sits 4,000 or dearly close to it. In this case, the way the numbers work out is 4,001 carrots. And to the left of the 4,000 carrots there sit 5,000 carrots, and to the left of 5,000 carrots in yet another storage facility there sits 6,001 carrots, and so on. We also see that the cost of moving the 4,001 carrots from this storage facility to this one will be this time what? How much? It will be 7 carrots per mile, because in 7 forward and backward trips we will be able to move 4,001 carats towards the storage facility where the 3,000 carats rest. Likewise, what is the cost of moving 5,000 carats to the nearest storage facility over here? Well, in this case, it will be 9 carats per mile, because in 9 forward and backward moves at 1,000 carats each, we will be able to move these 5,000 carats to this storage facility. Likewise, what is the cost of moving 6,001 carats from this storage facility to this one? Well, it will be 11 carats per mile, because evidently in 11 forward and backward moves, we will be able to transport 6,001 carats from this storage facility to this storage facility. So now we see that the cost of moving the corresponding amount of carats from the current storage facility to the next one grows or diminishes, if you will, as an odd positive whole number. 1 carat per mile, 3 carats per mile, 5 carats per mile, 7 carats per mile, 9 carats per mile, and 11 carats per mile. So now, where do these numbers that separate the consequent storage facilities come from? We already know the arithmetic for these numbers. For example, to compute the distance between this storage facility and this one, what kind of equation will we construct? Well, we already know it will be 4,001 carat minus 7 times x equals 3,000 carats. This is carats per mile, this is miles. This way we have 1,001 carats equals 7 times x. In order to compute the distance between this storage facility and this one, we construct essentially the same equation. 5,000 minus 9 times x equals 4,000. I'll use the letter K, 4,000, or dearly close to it, but you understand the arithmetic. 1,000 will be equals 9 times x. How do we compute the distance between this storage facility and this storage facility? In the same way. 6,000, or dearly close to it, minus 11 times x equals 5,000 carats, or dearly close to it. Again, we have 1,000 equals 11 times x, and so on. Every time we solve this equation for x over the set of whole positive numbers, we obtain the corresponding distances: 143 miles, 111 miles, 91 miles, and so on. It is a good idea for you guys to keep carrying this computation out and computing these distances as the storage facilities percolate to the left. In this respect, as a final thought for food for you guys, I have 2 things to say. First, befitting the specific problem-solving approach that we are discussing, the reverse order problem-solving approach, when we look at these arrangements of carats, storage facilities, and miles, what idea can visit us at some point? Well, the idea that can visit us at some point with respect to the reverse order problem-solving approach that we're studying right now is the following. Instead of consuming carats on our trip, for example, towards the market or towards the mile marker where we'll have no more fuel left, we can be gathering carats along the way. And if you argue that there is too much orchestration is required to grow carats over these long distances, that is fine. We can replace carats, for example, with mushrooms. We can start at the 0 mile marker and stipulate that as we travel forward, we pick up mushrooms at a given rate. For example, 1 mushroom per mile. And we can carry at any one time at most 1,000 mushrooms. Then the question is, at what maximal distance away from the 0 mile marker can we aggregate 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, and so on mushrooms. And again, it will be evident that the overall algorithm in this case will be mostly symmetrical. We'll start with 0 mushrooms at the 0 mile marker. We will travel along 1 mile at a time. We will pick up 1 mushroom, put it on the cart, move on. Here, by the looks of it, we will actually stop at the mile marker 999. 999. We will only take with us what? 666 mushrooms. As we travel along for 334 miles, 334 miles, we pick up 334 mushrooms. We put them on the cart. At that point, we reach the maximal payload capacity of the cart, 1,000 mushrooms. We dump them at an appropriate location. We travel back. We pick up 334 mushrooms. We load the remaining mushrooms that were left at that storage facility. We travel back. We pick up another 334 mushrooms. We arrive over here, reaching our capacity or something close to it, and we unfold the solution on and on. This is for you to think about and perhaps even develop further. The second thought for food that I have for you is the following. If we walk away from this problem a little bit and put on the hat that reads a physicist, then some of us may recall our classical mechanics course that we took in college, and specifically the equation of the ideal rocket. In the relativistic case, when the velocities are comparable with the speed of light in vacuum, the equation that we obtain for the rocket is the following. A sub 0 over m equals 1 plus v over c divided by 1 minus v over c raised to the power c over 2 v e. And in the non-relativistic case, the equation of the ideal rocket will be m sub 0 over m equals e raised to the power of v over v sub e, where m sub 0 is the overall mass of the rocket at the initial time. The mass m is the mass of the rocket and the propellant at a certain amount of time. Ve is the velocity of the exhaust gases with respect to the frame of the rocket, and v is, of course, the velocity of the rocket itself. This specific formula, even forgetting the technological challenges of the relativistic case, just in the classical case, what this equation tells us is that it gives us the ability to estimate the initial mass of the rocket, which we must have in order to achieve the velocity v. And this equation, actually, in the classical case, is already quite punishing in the following sense. Using the traditional chemical propellant, we know that intercontinental travel within the confines of our planet is definitely possible. It's not easy, but it is possible. We also know that based on the traditional chemical propellant, it is possible to travel from the Earth to the Moon. We already know historically that that rocket had to be very, very large. And again, it looks like that according to the numbers produced by this formula, it is very challenging, but perhaps possible to execute interplanetary travel based on this equation using the traditional chemical propellant. However, this formula over here is absolutely brutal and prohibitive when it comes to interstellar travel based again on the traditional chemical propellant, and this is fundamentally not happening. And again, roughly speaking, it means that even the small increments in the desired velocity mean that the initial mass of that rocket must be quite large. And here comes the food for thought for you guys to ponder. As we look at the numbers that we developed over here, what do you think? Do we have any relation to the rocket propulsion in this case, given, of course, the situation that with the rocket we move only in one direction, more or less. And in this case, we do a bunch of forward and backward motions, but fundamentally, do we have any sort of analogy with rocket propulsion, which means that in order to gain even small incremental gains in the, for example, distance from the 0-mile marker, do we need a very large increase in the number of fuel, or in the amount of fuel, or in the number of carats that we must have initially in order to accomplish or achieve this increment in distance? Think about it. And for now, this is it for the solution of this problem, and we will move on to our next challenge. Our next challenge will be an absolutely beautiful mathematical problem S2M11, in which we're given 9 nerve cells that are sprinkled over a circle. We're also told that each and every one of these nerve cells can be in only one of only 2 mutually exclusive states: excited state or not excited state. For demonstration purposes, graphically, we will depict a cell that is in the excited state with a solid red or pink circle as shown over here, and we will depict a cell that is in the not excited state with a hollow circle as shown over here. We're also told that in the colony of 9 nerve cells, precisely 4 cells are in the excited state and 5 cells are in the not excited state. It should be understood that the specific partitioning of the cells that are in the excited and not excited state doesn't really matter. Here I showed one for you guys just for demonstration purposes, but any other partitioning of the 4 cells that are in the excited state and 5 cells that are in the not excited state will actually do for the purposes of asking the question that we're about to ask. Now, let us imagine that on every unit of time, for example, every second or every minute or every hour, let's agree that every second, the colony transitions from one state into the next state according to the following rule. Every cell that is in the excited state, as depicted over here, sends 2 signals, one signal towards its right and one signal towards its left. And each one of these excitement signals propagates only to the nearest adjacent cell, and each such nearest adjacent cell consumes this excitement signal completely and in its entirety, and does not let that excitement signal propagate any further, as shown with this axis over here. Then, if a given cell, whether that cell is excited or not excited, will transition to the excited state according to the following rule. If such a cell receives a excitement signal only from one of its sides but not the other, only then it will transition into the excited state. For example, here I depicted the fact that any given cell can be in any given state, not excited or excited, by splitting that cell in half. But of course, we understand that I did it only for demonstration purposes. No cell can ever be in such a split state. It can only be excited or only be excited or only be not excited. As such, if a simple cell receives a signal looking down at the center of the corresponding circle from its right and not from its left, then it will transition into the next state of the colony and become excited. Likewise, if any given cell, be it in the not excited state or be it in the excited state, receives a signal looking down at the center of the circle from its left but not from its right, then it will percolate into the next state as excited cell. Further, if a given cell, whether that cell is not excited or whether that cell is excited, receives an excitement signal from both sides, then we agree that two such signals traveling in the opposite direction cancel each other out, and the cell will not, as depicted with the big X over here, will not transition into the excited state. And it should be understood that, for example, here in the sample configuration, this specific cell is in the not excited state. Obviously, it will not receive any signal from anywhere. That means that into the next state of our colony, it will percolate by staying in the not excited state. But, for example, let's look at this cell. This cell right now is in the excited state, but evidently it will not receive any of the excitement signals from anywhere, which means that into the next state of the entire colony, this specific cell will percolate as not excited cell. Once the state transitions explained over here are understood, for the sake of asking the question that we're about to ask, let us agree that the colony in general and in total is excited if in that colony there exists at least one excited cell, and likewise let us agree that a colony is not excited if all the cells in this colony are not excited. And here comes the question. If on schedule every second the transitions of the states of the cells in this colony take place as explained, and that colony is left to its own devices, the question is, will this colony remain excited indefinitely, or will there come a point in time when this colony will be not excited, meaning that will the excitement of this colony, if it's left to its own devices, peter out, subdue, and completely stop and disappear, and all the cells in this colony will be not excited. And that is what I captured with the symbols shown over here, t tending to positive infinity. That means that if we leave this colony to its own devices under an infinite time model, will the excitement of that colony live indefinitely for as long as we care to look, or will it peter out completely and completely stop? Think about it, and this is it for this episode. Thank you very much for watching. Thank you for your time. I will see you in the next episode, Season 2, Episode 9, where I will discuss the solution of the mathematical problem S2E8.